Welcome to The Explainer. Today, we're going to dive into some hidden chemical reactions that power pretty much everything, from your phone's battery all the way to your own body.
So let's kick things off with what looks like a magic trick. Have you ever been in a science class and seen a dark, vibrant purple liquid suddenly turn completely clear? It seems impossible, right? Well, today we're going to pull back the curtain and see exactly how it works. And to solve this little mystery, here's our game plan. We'll start with that magic trick. Then we'll meet the key players in the reaction. After that, we'll see how chemists keep score, and then we'll finally crack the case of the disappearing color. And trust me, it's pretty cool.
All right, first up, the chemical magic trick. Okay, so picture this. We've got this stuff called potassium manganate 7, and it has this incredibly deep, dark purple color. But when you mix it with something called a reducing agent, and don't worry, we'll get to what that is in a sec, poof, the purple just vanishes, gone. You're left with a totally clear solution. So, what in the world is going on at the atomic level? Well, it all comes down to one of the most fundamental processes in all of chemistry.
And that brings us right to part 2, meeting oxidation and reduction.
This whole process is called a redox reaction. And redox, well, it's just a mashup of two words, reduction and oxidation. At its very heart, it's all about one thing, the transfer of electrons. You can think of it like a little chemical handshake, where one atom passes an electron over to another.
And here's the absolute key. This is a two-part deal. It always happens at the exact same time. One substance loses electrons, we call that oxidation, and another substance gains those very same electrons, and that's called reduction. You can never, ever have one without the other. They're a package deal.
So how in the world do you remember which is which? Well, chemists came up with this really handy mnemonic, oil RIG. Oxidation is loss, reduction is gain, of electrons, of course. Just burn oil RIG into your brain, because it's the key to unlocking this whole thing. Okay, so if electrons are moving around, something must be making them move, right? And that brings us to our next part, the agents of change. Every redox reaction has two main characters, two key players, the oxidizing agent and the reducing agent. First up, the oxidizing agent. Now, the name is a bit of a giveaway, right? It's the substance that causes oxidation in something else. But, and this is the important part, to make another substance lose its electrons, the oxidizing agent has to be the one to take them. And what did we just say gaining electrons is? Reduction. So the oxidizing agent is the one that actually gets reduced. And, you guessed it, on the flip side, we have the reducing agent. It does the exact opposite. It causes reduction in another substance. And it does that by being the electron donor. It gives its own electrons away. And because it's losing electrons, well, you know the rule from oil RIG, the reducing agent itself gets oxidized. See? They're perfect mirror images of each other. And this really shows you just how perfectly these two work together. You've got the electron donor and the electron receiver. One can't do its job without the other. As one gets oxidized by giving away electrons, the other absolutely has to get reduced by taking them. They're locked in this perfect chemical dance. It's their partnership that makes the whole reaction possible. But you might be wondering, how do chemists keep track of all these electrons flying around? I mean, it seems kind of complicated. Well, that brings us to our next section, keeping score with numbers. We're going to look at a cool little bookkeeping tool called oxidation states. So, chemists have this system called oxidation numbers, or sometimes you'll hear oxidation states. Honestly, the best way to think about it is as a set of bookkeeping rules for electrons. It's basically a number we assign to an atom that tells us, sort of hypothetically, how many electrons it's gained or lost. And the good news is, there are some pretty simple rules for this. For example, any element just hanging out by itself, its oxidation number is 0. Easy. For a simple ion, the number is just its charge. And then we have some standard go-to numbers for common elements like oxygen and hydrogen. But the most important rule of all, in a neutral compound, all those individual numbers have to add up to 0. You got to balance the book. So let's actually put this to work. We can take a compound like this one. We apply the rules we know for potassium and oxygen. Then we set up a little bit of simple algebra because we know the whole thing has to equal 0. And when you solve for that unknown chromium in the middle, voila, we figure out its oxidation state is +6. This is the exact kind of detective work we need to solve our purple mystery.
All right, it is time. We have our concepts, we have our suspects, the agents, and we have our scorekeeping tool. Let's go back to the scene of the crime. Section 5, solving the mystery of the vanishing color. Okay, remember that deep purple solution? The color comes from one specific thing, this ion right here, called the manganate 7 ion. And you can see that manganese atom sitting right there at the center. Now, if we use the rules we just practiced to calculate the oxidation state of that manganese atom, we get a whopping +7, a really high number. And that, my friends, is the secret. It's that very specific +7 oxidation state that's responsible for the intense purple color. Now, it turns out this ion is a really, really strong oxidizing agent, which means it's going to do what? Come on, you know this. It's going to get reduced. And in this particular reaction, it gets reduced in a big way. It gains a full 5 electrons from whatever it's reacting with. So this flood of 5 new electrons comes rushing in, and it fundamentally changes the manganese atom. It's completely transformed. It goes from being part of that big, complex ion to becoming a much simpler one, the Mn2+ ion. And its new oxidation state, just +2. And here is the big reveal, the punchline. The Mn2+ ion is basically colorless in water. So there you have it. The magic trick wasn't magic at all. The color vanished simply because a transfer of electrons changed the oxidation state and the identity of the manganese atom. But this is way more than just a cool lab demonstration. Redox reactions are, and I mean this literally, happening everywhere. They're happening inside of you right now. Let's talk about why redox matters. I mean, seriously, just think about it. The combustion that burns fuel to power a car, that's a super fast redox reaction. The battery in your phone, that's just a carefully controlled redox reaction releasing energy. And you, the way your body gets energy from food is just a long, complex chain of these electron transfers. From the rusting of a nail to the way plants make the oxygen we breathe, it is all redox all the time. So the next time you see a fire burning, or check your phone's battery, or even just take a breath, remember that silent, powerful transfer of electrons that's at work. And it really makes you think, doesn't it? If this one invisible process is responsible for so much, what other incredible chemical engines are quietly shaping our entire world right under our noses?